Good afternoon, one and all. On the behalf of Pratap University Jaipur, I welcome you all at our FDP session. Now I would like to call our Dean Academics, Dr. Gaurav Sharma, for greet the participants.
Everyone, it is an honor and privilege for me to welcome you on behalf of Pratap University to this FDP session, the lateralization organized by School of Pharmaceutical Sciences. Now I would like to invite Dr. Kannadasan, Principal, School of Pharmaceutical Sciences, to give welcome speech. Thank you.
Good afternoon to all. Today we are organizing the topic of industries pelletization faculty development program on the behalf of Pratap University and Chairman, Honorable Vice Chancellor, and the Dean Academics, and on the behalf of faculty members, those taken the initiatives this program to be successful. I welcome all, and most importantly, I invite the different cadre of participants, whether faculty members, research aspect. I welcome all to the successful program, and that is pelletization, the recent development, everything in the pharmaceutical sciences. One, I welcome all you. Thank you.
Thank you, sir. Now I like to call Mr. Prem Kumar, Associate Professor from Department of Pharmacy, for profile of the resource person.
Good afternoon, everyone. So, a warm welcome to one-day FDP program, which is organized by Pratap University, Jaipur. So it's my privilege to introduce today's speaker, Dr. MD Athar Alli, Assistant Professor, SAM, Higginbottom University of Agriculture and Technical Sciences, Prayagraj. Sir has 17 years of experience. It includes 15 years of teaching and 2 years of industrial experience. Sir has completed his PhD in the year of 2012. So presently, Sir working as an assistant professor, and Sir was published 3 books, and 1 book is under publishing. And Sir has published more than 28 papers in international and national peer-reviewed journals. And also, Sir has attended as a speaker in so many various conferences attended by different organizations. So now I'll hand over to session to Gaurav Sharma.
Thank you, sir. Now I call our Dean Academics to introduce our Honorable Vice Chancellors.
Professor Abhay Kumar has acquired his PhD degree from the Department of Business Management, HNB Garhwal University, Srinagar. He had completed his MBA from Motilal Nehru Institute of Research and Business Administration, University of Allahabad, in the year 1980. Professor Abhay Kumar has a total work experience of more than 39 years. He has been an entrepreneur for 3 years and worked in the industry for over 16 years as a senior manager personnel. However, he has keen interest in the field of marketing management, strategy being his forte. He has more than 20 years of experience in teaching and research. He had a good number of research papers published to his credits. He has organized and chaired several national and international conferences, seminars, workshops, symposium, and colloquium. He has also been the keynote speaker, chief guest, and the member of conferences, seminars, and been instrumental in the organization of various FDPs and MDPs. He is also a member of numerous bodies related to higher education and in Board of Management Advisory Board, as well as a member of BOS and RDC of a good number of institutes and universities. Some examples are nominated as WES ambassadors, higher education for 15th World Education Summit, Mumbai, organized by LS Technomedia Private Limited, member advisory board of Lexicon Management Institute of Leadership and Management, Pune, awarded outstanding contribution by VC to education sectors by ASCOP, member National Committee of SITI Innovation Research Organization. Professor Abhay Kumar has actively promoted institutional branding during his career and has been instrumental in successfully introducing the concept of mentorship at the institute level in the past. He has vast experience in training, motivating, and counseling the students, fraternity, and faculty members. Now, I would like to invite Honorable Vice Chancellors to give special address to the FDP sessions to the participants. Thank you.
Well, I would like to extend my sincere thanks to Dr. S.K. Mohammad Athar Ali from the Department of Pharmaceutical Sciences, SIHAS. In fact, as you have just listened, I myself have been a product of the University of Allahabad, so it gives me great pleasure once more to welcome Dr. Athar Ali. I am really very thankful to Dr. Shanmugam, Dean Academics, Pratap University, the Principal of the School of Pharmaceutical Sciences, Dr. Kannadasan, Mr. Gaurav Sharma, the Coordinator, Mr. Prem, Mr. Arvind, who is looking after the entire IT setup here. So this FDP is going to be a landmark in the learning process, not only by the participants, the faculty members, and other say people attending today's faculty development program, but myself as well. So it is with great pleasure that I would hand over the entire setup to Dr. S.K. Mohammad Athar Ali now, and I'm very sure we would all profit from what he says. Thank you so much.
Thank you, sir. Now I invite our resource person, Dr. Akhtar Ali, to start his session.
Myself is grateful to the administration of the Pratap University, Jaipur, for giving me an opportunity to deliver my presentation on the pelletization technology. Good afternoon, everybody. I am here to present on the pelletization technology. This presentation is basically summarized into introductory part, advantages and disadvantages, pelletization techniques or process, layering process, that is based on the fluid bed processing, raster technology, that is also called rotogranulation, extrusion, spheronization, globulation, melt extrusion, spherical agglomeration, that is also called balling, 3G pelletization, cryopelletization, and lastly your characterization. First of all, I have to give an introduction on the pelletization. Pelletization is Pelletization can be defined as an agglomeration or size enlargement process that converts fine powders or particles of bulk drugs and excipients into small, free-flowing and spherical units that is termed pellets. Pelletization involves the manufacture of agglomerates with a narrow size distribution range, which is usually within the mean size from 0.5 millimeter to 1.5 millimeter. Pellets have free-flowing properties that can be coated and usually used in controlled or modified release forms. Next, come to the agglomeration, granulation, and pelletization. These are the general terms that are used synonymously, and no clear distinction is made between them. In general, the size enlargement process producing agglomerates is termed agglomeration. Generally, if agglomerate size distribution is within the size range of 0.1 millimeter to 2 millimeter and have high porosity of about 40 to 50%, the process may be called granulation. If the agglomerates have a narrow size range, usually with mean size from 0.5 millimeter to 1.5 millimeter and have a low porosity, that is of about 10%, with free-flowing properties, then the process is called pelletization. The basic difference between your granulation and pelletization is, in granulation, the particles may not have spherical shape, and in pelletization, the particles must have spherical shape and must have free-flowing properties. This is the basic difference between granulation and pelletization. Other factors are related to your porosity. In case of granulation, it is around 40 to 50%, while in case of pelletization, it is about 10%. Process resulting highly spherical agglomerates of narrow size distribution termed pelletization process. Conversely, it is termed as granulation process. Friends, if we are getting a spherical agglomerates of size distribution from a process, then it will become pelletization. Alternately, the process will be termed as granulation process. And likewise, your granulation process yielding highly spherical agglomerates of narrow size distribution be considering as pelletization process, while an unsuccessful pelletization process may be considering as granulation process. In this slide, I have tried to present the difference between In this slide, I have tried to present the differential agglomeration, granulation, and pelletization process basing upon the parameters like your shape, size distribution, size range, porosity, and flow property. For agglomeration, the shape will be irregular, while for granulation, it will be somewhat spherical, but in case of pelletization, it must be highly spherical. And the size distribution is wider in case of your agglomeration process and intermediate for the granulation process, while it must be narrow for the pelletization process. Accordingly, the size range for the agglomeration have no defined size range. For the granulation, it will be between 0.1 to 2 millimeter, and for pelletization, it will be between 0.5 millimeter to 1.5 millimeter. And porosity, related to porosity, in case of granulation, porosity is high, and it is for granulation, it will be between 20 to 50%, and for pelletization, it will be about 10%. And flow property, in case of your agglomeration, it will be very poor. It will be very poor in case of agglomeration, and in case of your granulation, it will be low, and in case of pelletization, it is high. Next, come to the advantages. Advantages of the pelletization technology can be studied on the several headings like your therapeutic effects. Pellets reduce peak plasma fluctuations and minimizes potential side effects.
eliminates irritant effects of some drugs on the gastric mucosa. Pellets-based modified release delivery systems are multi-particulate systems, thus limits localized build-up of drug and are less susceptible to dose dumping than single-unit dosage form. Here your dose dumping issue may be poor. In case of pelletizer, dose dumping issue will be to some lesser extent, and this can be dispersed freely throughout the GIT, so its absorption will be high. Can deliver incompatible bioactive agents and reduce intra-patient variability. This is a major issue related to your performance of the dosage form. Next, come to the pharmaceutical advantages. The most important pharmaceutical advantages achievable from the pelletization technology is its controlled release application. Pellets have the ideal low surface area to volume ratio that provides an ideal shape for application of coating for achieving controlled or modified release profile. Means pellets have ideal low surface area to volume ratio which is suitable for application of a coating, and this coating results in controlled or modified release profile. Other benefits are your uniformity of dose or content, improvement in handling properties to the excellent flow property, prevention of dust formation, increases bulk density and decreases bulk volume. So the final volume of the dosage form will be small. Defined shape and weight improves appearance of the product. This is related to your elegance of the product. Next, come to the disadvantages. This is an expensive process and requires highly specialized equipment. The process is complicated one and requires too many process variables as well as formulation variables. Means the processing is a complicated one which is requiring monitoring of many process variables and your formulation variables, which I will discuss on the later part. Often pellets cannot be compressed into tablets because they are too rigid or deformed during the compression process. Means it is in some cases we cannot compress the pellet into the form of tablet because during the compression process either they will deform or these pellets are too rigid, so they cannot be compressed. In that case, we have to present the pellet in the form of a capsule. In that case, we have to present the pellets in the form of capsule. The control of the production process is difficult. For instance, the amount of water to be added is critical for the quality of the pellet, and overweighting can occur very easily. Means during production process, if we are changing some of the variables related to your formulation, then we will not get a pellet. Rather, we will get a granulation and the process will become a granulation process, and the pelletization process will be a unsuccessful one. Okay. Then, what are the different pelletization technologies that are available so that we can use them for preparing pellets? First is your layering process. The layering process is basically performed with the fluid-based processor. And this accordingly the process is called fluid-based processing. Layering process can be achievable using solution layering, suspension layering, dry powder layering. We can go for layering process by using a solution, a suspension, or a dry powder. Next is your extrusion sterilization process. Third is your globulation. Globulation can be achievable using a spray drying process, spray congealing process. Next is your melt extrusion. After that comes spherical agglomeration, which is also called balling. Balling can be achievable using liquid-induced agglomeration or melt-induced agglomeration. Next comes precipitatation. Precipitatation can be performed with precipitator 1 and precipitator 2. And lastly, your cryopelletization. Next, come to the layering technique. What is layering technique? It is the most well controlled and straightforward process. It is most well controlled and straightforward process. The layering process comprises The deposition of successive layers of drug entities from solution, suspension, or dry powder on a nuclei which may be crystals or granules of the same material or inert starter sheets. Means the layering process is comprising of depositing successive layers of drug entities, which may be in the form of solution, suspension, or dry powder onto a nuclei, which may be a crystals or a granule of the same material or an inert starter sheet. If we are using an inert starter sheet, then it is called pellets. Layering technique is of following categories as I have discussed earlier, that is your solution layering, suspension layering, and powder layering. The basic principle of layering technique involves fluidized bed processing, in which the particles are fluidized and the coating or binding fluid sprayed on them, and then it is dried. Means we have to maintain the particles in the fluidized state, and in this fluidized state we have to apply the coating or binding fluid, and which will then get dried. Cycling of spraying step followed by drying step is continued until the desired layers of drug or polymer is formed. Means we have to go for spraying step, then we have to follow the drying step. After that, then cycling has to be gone to this spraying step and then drying step. And this process will be continued until the desired layer of drug or polymer is formed. Yeah, means we have to form the layer of drug or polymer on the starting material to the desired level. Small droplets and low viscosity of the spray medium ensures an even product coating or pelletization. If your droplet size is small or your viscosity of the spray medium is low, then we can achieve an even product coating or pelletization. Next, coming to the solution layering. In this process, the drug substance, binder, and other excipients are dissolved in application medium that is spread onto the fluidized core or starter sheet material, usually a coarse crystal or non-ferrous. Means we have to prepare a solution of a drug in binder solution, and we can include other excipients in that solution. And this solution is then spread onto the fluidized core or starter sheet. And as I have discussed, means application of fluid then followed by drying has to be continued. Cycling of the application of fluid followed by drying has to be continued till we are getting the pillars of desired shape and size or wished properties. Okay, next come to the suspension layering. In this process, the drug substances dispersed. The drug substances dispersed in the solution of a binder. And in this dispersion, we can also include excipients. And this suspension is then spread onto the fluidized core or starter sheet material. Means this suspension has to be spread on the fluidized core or starter sheet material, and then this has to be dried. And cycling of spraying process and drying has to be continued till we are getting the pillars with desired properties. Okay. Next, come to the powder layering. The layering process is performed using a drug powder and a binder liquid instead of using a solution or suspension of drug in a binder solution or suspension. Means here your starter material will be drug or blend of the drug and excipient. Means the powder bed will comprise of drug and drug or a mixture of drug and excipient. Onto this powder bed, which is in fluidized state, we have to apply the binding solution. By spraying. As this process will continue, what will happen? The particle will start agglomeration. The particle will get agglomeration, and subsequently your size enlargement process of the agglomeration will go on, and we will get the particles of the desired shape and size. Basically, powder layering is done with a special technique, that is rotogranulation. Okay, that is, we have to use the rotary process. Next, come to the fluid-based processors. Fluid-based processors are used for processing the processing in fluidized state. Means we have to keep the material in fluidized state and we have to go for process. Okay, and these are having applicability in the fluidization process, so it comprising the part of the presentation. These are basically of three categories. One is your top spray process, bottom spray process, that is also raster process, and your tangential spray process, that is your rotary process. As it is depicted from the figure, in case of top spray process, the sprayer is at the top. The sprayer is at the top. But in case of bottom spray, the sprayer is at the bottom. At the bottom, and here additional one tube is there, within which the spraying spraying or application of binding fluid is restricted, and this tube assists in movement of the particles. This tube assists in the movement of particles to this and cycles the particles between the coating zone and your drying zone. This is the coating zone and this is the drying zone, and this is also drying zone. And your fluidizing air is inletted from the downside. And in top spray process and bottom spray process, the processor are having a perforated base through which your fluidizing air and drying air will enter into the processor. Through which your fluidizing air and your drying air will enter into the process. And in case of tangential spray, here a circular rotating disc is used. And there is a gap between the circular disc, periphery of the circular disc, and your outer periphery of the processor here. And through which the drying air is entered into the processor. Means the drying air will enter into the processor through this gap. And accordingly, it will create a turbulence motion within the powder bed. Okay. Next, come to the process variables. Process variables which of importance are your fluidizing air flow, fluidizing air humidity, fluidizing air temperature, spray rate, column height, nozzle and peristaltic pump, atomizing air, particle size. Product variables include pore particles, particle surface, particle size, solution viscosity, and your solution viscosity and your solution of solid concentration. Equipment variables are your base plate type, nozzle size, filter bed type, and your model of equipment. These are the process variables, product variables, and equipment variables which play important role in the reproducibility of pelletization process. Means our pelletization process, to keep the pelletization process reproducible, these process variables has to be monitored within a specific range. Alternately, our product's performance will get changed. Next, come to the tangential spray process. Here, important is your parameters which are monitoring the performance of the process. We have to discuss it. I am presenting the parameters which are monitoring the performance of the process. First is your liquid addition rate, inlet air temperature, humidity, atomizing air pressure, binder type and your concentration, disk speed, and your disk gap. Tangential spray process has applicability in the powder layering process. This technique is basically suitable for powder layering process. Means if our starting method means drug itself is a powder and it is acting as a starting material for pelletization process, then this process will be suitable. Factors affecting the powder layering process are your powder delivery rate and your flow characteristic of the powder. Next come to the rotogranulation, which is the other name of the rotary process. Okay, this is a single unit pelletization process, and it is also called centrifugal granulator, rotary fluid bed granulator, rotary fluid bed processor, rotary processor, and your rotor granulator. Okay, and this rotogranulation process basically has follow steps. That is your pre-blending of the formulation powder. Means we go for pre-blending and of the formulation powder, including the active ingredient, fillers, disintegrants, and a flow of layer. In a flow of layer means the pre-blending will be performed by the flow of air. Flow of air. Here we should not rotate the base plate. Means we will not rotate the base. Okay. The granulation of the mixer by spraying of suitable liquid binder onto the fluidized powder bed. Then we have to apply the liquid binder by spraying technique onto the powder bed, which is in the fluidized or suspended state, and accordingly granulation process will proceed. Next is the drying of the granulated powder to desired moisture content. Then we have to dry the product so as to get the desired moisture content that will be suitable for the further processing. During processing, three mechanical force causes particle movement, mixing, granulating, drying, and coating with good content uniformity. First is the spinning of the disc generates a centrifugal force. Second is a lifting force is generated by the hot air as the hot air passes through the adjustable disc gap. Third is your gravitational force that causes material to fall down onto the disc. Next, come to the extrusion and sterilization process. This is a multi-stage process for obtaining pellets with uniform size from wet granulate. Okay, means we have to use a wet mass so as to prepare the pellets, and this is a multi-stage process. As the name indicates, it comprises of two stages. One is your extrusion and your sterilization. Extrusion is the first step where we are extruding the wet mass to form a rod-like structure. Okay, and and the size of the sphere is determined by the diameter of the extruded used. Okay, for example, in order to obtain spheres with a diameter of 1 millimeter, a 1 millimeter screen is used for extruding the wet or plastic mass. Next step is your sterilization. Sterilization is the process of forming a spherical particle from the rod shape extruded that has been obtained from the extrusion stage. Okay, the extrusion sterilization process involves following steps. One is your dry mixing, massing, that is your wet or thermoplastic, extrusion, pelletization, that is also called sterilization, drying, and screening. Screening is the optional step in case of your extrusion and sterilization process. Next, in this, I am presenting the schematic flow chart of the extrusion sterilization process. First of all, we have to mix the active and excipient in a standard mixture, and in this standard mixture, we have to add the your binding fluid so that it will be converted into wet or plastic mass. If the binder is a meltable binder, then we have to use heat. We have to take the assistance of heat so that it will be converted to a plastic mass. And this plastic mass has to be extruded in an extruder. And this extruded has to be subjected in a sterilizer so as to get the wet or plastic fillet. And in dryer, we will dry the wet fillet only, not plastic fillet. If it is a plastic fillet, then we will not dry. But if it is a wet fillet, then it will be dried in a dryer to the desired moisture level. Okay. Then in this slide, I have tried to present the different stages of the extrusion and sterilization process. First is your dry mixing. Dry mixing of the ingredients is done in order to achieve homogeneous powder blend. Then we are doing the dry mixing to get a homogeneous powder blend. Then we have to go back. Next step is your wet or thermoplastic massing. The powder are there. This means powder dispersion is subjected for wet or thermal mixing. Subjected for wet or thermal mixing to form a sufficiently plastic mass. And the most commonly used granulator for wet massing is your planetary mixer, sigma blade mixer, high shear mixer, that is also called RMJ, and covert mixer. Next comes the extrusion stage. In this stage, the wet or thermoplastic mass is shaped into cylindrical segments, that is rod shaped with a uniform diameter using extruder that may be screw, screen, or gear type extruder. Next is your sterilization stage. The long segments that has been that is rod shape that has been obtained from the extrusion stage are broken into small segments that are rolled to get solid particles, that is your spheroids. And next is your drying. Drying of the spheroids is done in order to achieve the desired final moisture content, and screening step is optional, which is done to separate the fillets with desired size distribution. Next, come to the extruder. Extruder basically comprising the extruders that are having applicability in filtration techniques are screen or basket extruder, gear extruder, and your screw extruder. Screen or basket extruders are produced low density extruders, and these are, but this process is having relatively high flow output. The gear extruder produces relatively highly dense fillets, and gears are robust and last longer, so gear extruders are having lower wear and tear. Screw extruders, these are commonly used in the industrial application. These are having industrial application. And in the case of screw extruder, the high pressure and heat is generated within during the extrusion process, so it is unsuitable for the thermolabile product. If we have to deal with thermolabile product, then we have to monitor the pressure by jacketing. Monitor the temperature by jacketing process. This is the schematic diagram of the wet extruder. This is the schematic diagram of the hot melt extruder. Here you can see heat and jacketing assembly is available so as to maintain the temperature of the extruder. Next is sterilizer. The basic machine consists of a rotating friction disc designed to increase the friction with the product, which spins at a high speed at the bottom of the cylindrical bowel. Means it is a sterilizer comprising of a cylindrical bowel. At the lower part of this cylindrical bowel, there is a rotating friction disc which rotates and which causes the spinning of the extrudes. The spinning friction disc has a carefully designed groove patterns on the processing surface. This is the most often processed, but several sizes and other types are also available. Means the spinning friction disc is available in several shapes and sizes with several designs. As the friction disc rotates, rod-shaped extruders move in the rotational movement or Uber movement, resulting the break of longer rod-shaped segments into smaller segments, which is then transferred into spheroids. The most important part that rod-shaped extruders should not be friable, but it should have a plastic property to have the ability to be spheronized. The edges of the cylindrical granules are the most fragile part, and this will generate the dust during handling. So we have to take discussion in regarding this issue. And here I have presented the principle and stages of pellet formation during extrusion and sterilization process. Means first of all we have got the extruded product from by the extrusion process, and this is subjected for breaking, which is done in sterilizer. In this stage, the speed of the sterilizer is quite low. And gradually we have to increase the speed of the sterilizer so that it will proceed for the sterilization process, and this is the intermediate step, and finally we are getting a highly spherical particle which is with no your porosity. Okay, these are the figures of the sterilizer. This is the sterilizer. This is the bowel in which we have to go for sterilization operation. This is the process. This is the process. This and this is the radial type. Okay. Next is your parameters. Parameters affecting quality of pellets. Equipment parameters are your mixer, extruder, extrusion screen, friction disc or plate, and in case of your friction disc or plate, disc group geometry, disc diameter and speed. Process parameters includes your extrusion speed, extrusion temperature, sterilizer flow, that is your disc flow, is material, how much material has been loaded on the disc, sterilization speed, that is the speed, disc speed, that depends upon the motor, sterilization time, that is the retention time, means how much time we are subjecting for sterilization step. Next is your drying method. In this important parameter, means we have to consider means what is the role of disc speed. There is an optimum disc speed and load for each disc diameter. Means we have to maintain the disc speed and disc load for each disc basing upon its diameter. If the momentum of disc is too low, then extruder will not densify sufficiently and no sphere will be formed. Means we will not get pellet, we will get granules. If the momentum is too high, this may be resulting from the underloading or too much speed of the base, then it will lead to granules fracturing. Means granules will get fractured, and too much force on the granules results in densification, which may deform. Compression of the particles within the granules. Sometimes some particle will get compressed into the granules, so its surface will deformed and it will not appear. Its appearance will get dim, and your minimum porosity. Here we will get minimum porosity. The disc group geometry also plays important role. Both radial and cross-hatch will work efficiently. Yes, we can use both radial and cross-hatch pattern. Radial disc has gentler and more controlled action, while radial will not suitable for the larger diameter disc. If your diameter of the disc is high, large, then we cannot use radial pattern. Retention time. Typical retention time to obtain sphere is 2 to 6 minutes. A sterilization with short retention time can help to reduce dust generation to a significant level. Okay, means we have to go for sterilization between 2 to, means we have to go for sterilization step that will be between 2 to 6 minutes, and sterilization with short retention time will reduce dust generation. Okay. Next, come to the globulation. Globulation process involves formulation of the globule, which will then converted into the pellets by drying. Okay. Means in this process we have to use the fluid of the drug and your excipient along with your bond. We have to use fluid that may be solution or your dispersion. this fluid has to be atomized in a drying chamber. And this automation process converts the fluid into droplets, which will then subsequently dried by the drying air that is present in the chamber. Okay, and this process requires keeping the droplet size small to maximize the rate of evaporation of basing upon the nature of your starting material. The process can be spray drying or spray concealing. Okay, if we are using a meltable binder, then we have to go for spray concealing. If we are using a meltable binder, then we have to go for spray concealing. In spray drying, we have to atomize the drug in a solution of suspension form. In the solution of suspension form, and this automation leads to spraying, which will subjected for hot air treatment, and then the product will get dry and we will get highly spherical particles. In the spray congealing process is similar to spray drying, also called spray chilling. In spray congealing, the drug is allowed to melt, disperse or dissolve in a hot melt of gums, waxes, fatty acids or other low melting solids. The dispersion is then sprayed into a stream of air and other gases with a temperature below the melting point of the formulation component under appropriate processing conditions. So we will get a spherical congealed pellets. Okay. This is the schematic flow diagram of spray congealing process. You can see here we are atomizing so that it is getting sprayed. It is getting sprayed and it is a closed vessel, conical shaped closed vessel. This is the atomizer. By the automation, we are converting the liquid into your fine droplets, and here it is get dry, and this is the collector which will separate the product from the gas or air, and this is the feed stock from which your material will get entered into the or pumped into the atomizer. This is applicability. These are having applicability of controlled release pellets, and this can be employed for improving the visualization rate and bioavailability of poor aqueous soluble drug, suitable for thermolabile pharmaceuticals like your amino acids, antibiotics, ascorbic acid. And here the particle size and size distribution, bulk density, porosity, flowability, and moisture content can be easily controlled by the design and operation of the spray. Next is the melt extrusion process. I have discussed in the extrusion process. This is also similar to that one. In melt extrusion process, we have to use the meltable binder. We have to use the meltable binder, and the drug has to be fed. Drug has to be fed along with your meltable binder for this feeding zone. And while the screw rotates, this will pump. This will move the your binder along with your drug and your excipient towards this side. And here the temperature is increased gradually. Here temperature is increased gradually by heating cartridge, and this will transform the extruders into a. Sorry, this will transform the material into a extruder, and then this is to be subjected for vaporization. Means here the hot melt extrusion is basically used for massing of the product so that its bulk density will be decreased, and we will get pellets with lowest porosity. We get the pellets with lowest porosity. Okay. Next is your spherical agglomeration. This is the boiling process. This pelletization process involves converting powders to spherical particles by continuous rolling or tumbling action on addition of an appropriate quantity of liquid or on application of high temperature. Means we have to roll or tumble the material in a continuous way. And during this rolling or tumbling operation, we have to apply the binding fluid, which may be a liquid or maybe a meltable binder. If we are using meltable binder, then we have to increase the temperature of the processor so that the meltable binder will get converted into liquid form, and accordingly our size enlargement process will proceed. This process is of two types. One is a liquid-induced agglomeration and well-induced agglomeration. The process comprises of liquid-induced agglomeration and a well-induced agglomeration. Liquid-induced agglomeration involves addition of binder liquid to the powder before or during the agitation stage. Means we have to add the binder in the form of a liquid, and this has to be added during the binding during the agitation stage or before agitation. In case of melt-induced agglomeration, we have to use a melt.
Sir, your mic is muted.
Is audible, sir? Hello?
Yes, sir.
Hello, yes, sir, you are audible.
Next is precipitation. This technique involves introducing a molten solid carrier along with your dispersed active ingredient as droplets into an inert and immiscible column of liquid. Droplets, upon introducing into the liquid column, moves either in upward or downward direction depending on their density with respect to the liquid in the column and solidify into spherical figures. Carrier sweeting may be a hydrophilic or hydrophobic one and should be solid at room temperature and have a melting point below 100 degrees Celsius. They may be melted at a temperature between 5 to 10 degrees Celsius, higher than the melting point of the carrier solids. These are having advantages over other pelletization methods in terms of quality, process cost, and improvement of and involvement of least process variables. Pellets produced by this technique are spherical in shape with narrow size distribution range and do not require drying. Here I have tried to present the equipment that are used for 3D pelletization. Basically, we are using 3D pelletizer 1 and 3D pelletizer 2. In both the apparatus, there is a column which is divided into two portions. One is the initial portion and second is the cooling portion. Okay, from the initial portion, the molten solid carrier is introduced and is maintained between 45 to 100 degrees Celsius. In the cooling portion, solidification of droplets occurs, which is maintained between 0 degrees Celsius to minus 40 degrees Celsius using cooling mixture of acetone and dry ice. The selection of equipment depends upon the density of the molten solid carrier. If density is low, then we have to use 3D pelletizer 2. If density is high, then we have to use 3D pelletizer 1. This is the figure of 3D pelletizer 1 and 2. Okay. Here, this is the 3D pelletizer 1. Here it is the initial part. It is the initial part as I have discussed in earlier. As I have discussed earlier, the initial portion and your pooling portion. So the initial portion and your pooling portion. Here it is the, this is the initial portion, and the material has to be fed from the top, and this is the pooling portion, and here the material will get solidified and accordingly get collected here. And this is the precipitator 2. This is the precipitator 2, and this is the initial portion. This is the initial portion, and this is the cooling portion. Means here cooling will be done, and here we have to maintain the temperature between 0 degrees Celsius to minus 40 degrees Celsius, and the material has to be fed from the bottom, and the product will get collected at the top. So this pelletizer is suitable if the density is low, and this pelletizer is suitable if the density of the carrier is higher. Okay, next is the pelletizer 1. In this type, the molten solid carrier are introduced from the upper portion as I have discussed earlier, and carrier portion of the column and the carrier solidified at the bottom portion, suitable for the hydrophilic solid carriers having density more than that of the liquid used in the column. Solid carrier which is having applicability in the pelletizer 1A are high density and hydrophilic. Example is your polyethylene glycol, polyvinyl alcohol, low melting for sugars, dextrose, maltose, and liquids suitable for column are low density oils like your mineral oil, vegetable oil, and your silicon oil. This is then is the pelletizer 2. In this type, the molten solid carrier are introduced from the bottom portion of the column and carrier solidified at the top, suitable for hydrophilic solid carriers having density low as compared to the liquid used in the column. Solid carrier used are low density and hydrophobic. Means low density and hydrophobic material can be used as solid carrier. Examples are glycerol pennate, glycerol palmostyrene, and glycerol monosterate. Liquids suitable for column are hydrophilic and high density like your ethyl alcohol, liquid polyethylene glycol, glycerin, and your water. Next is your cryopelletization. In this process, the droplet of the solution or dispersion are converted into solid spherical particles or pellets using liquid nitrogen as the fixing medium. Means we have to use the liquid nitrogen so as to solidify the particles, spherical particles, and to get the pellet. Means first of all, we have to convert the solution or dispersion of the material into droplets, and this has to be interacted with the liquid nitrogen, which will fix the particles or your spherical particle, and we will get the pellet. The pellets are produced when the droplets encounter liquid nitrogen at minus 160 degrees Celsius, which solidifies. Then they are dried in conventional dryer to remove the water or organic. This technique is suitable for immediate or controlled usage pellets. The amount of liquid nitrogen required for manufacturing depends on the solid content and temperature of the solution or suspension being processed. The equipment consists of a container equipped with perforated plates, reservoir of liquid nitrogen, conveyor belt with transport cables, and storage container. Next is factors affecting pelletization technique. These are the factors which affect pelletization technique, like your moisture content, rheological characteristics, physical properties of the stacking materials, availability of drug and excipient in the binder fluid, composition of binder fluid, extrusion characteristics, speed of the sterilizer, drying technique and drying temperature, desired properties of the pellet. Next, come to the characterization of the pellets. We can characterize pellets based upon their size distribution, shape, surface morphology, specific surface area, density, porosity, tensile strength, hardness, resolution. And these are all about my presentation. Thanks for your patience hearing. If any queries, please.
Participants, if you have any query, you can ask. Spanda sir,
Yes, can I ask questions, sir?
yes sir, you can ask. Sir.
Okay. Thank you, sir. It was a very wonderful presentation, sir. Actually, I am Simanchal Panda from Pharmacy Department. Sir, actually, I am having one query that what may be different defect of pelletization techniques and how that can be overcome. And the second question is that can we formulate sustained release double layer tablet and taking one layer as the pellet?
One layer as a pellet. It can
Yes,
be
sir.
possible, sir. It can be possible.
Okay, sir. And sir, actually, I just want to know few defects as there are different formulation. If you're going for the emulsion, we are generally getting the cracking, creaming. If that is for the tablet, sticking, mottling. So likewise, if there is any kind of processing defect for during the formulation of pellets, sir.
Basically, if our surface morphology will get changed, if surface morphology will get changed, then the product's performance will get changed, and this has to be monitored. And your particle size, specifically particle size, plays important role in the performance of the pellet. So this has to be monitored by maintaining the proper process parameter, product parameter, and your equipment parameter, as applicable in case of your fluid-based processor or your extrusion and sterilization process. But related to your defects, to my level of knowledge, I have not got any report related to studying defects of the pellets. To level based of my knowledge, I have not encountered such kind of issues.
Thank you, sir.
Hello. Anybody have a question? Yeah, you can ask to sir. Okay, now I invite our Dean Academics for the vote of thanks.
Good afternoon. An ignited mind is the most powerful weapon on the earth, above the earth and under the earth, and this is not go through education. As all good things come to an end in FDP webinar, on behalf of Pratap University, I take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this FDP organized by our School of Pharmaceutical Sciences. At the outset, I thank our resource person, Dr. S.K. Mohammed Athar Ali. We are really enlightened with your knowledge and presence. We are thankful to our Honorable Founder, Sri Ram Singh Bahaduria, our Honorable Chancellor, Mr. Shailendra Bahaduria, for their motivation. I would like to thank our Honorable Vice Chancellor, Professor Dr. Abhay Kumar, for his enthusiastic support. I would like to thank to Dr. Kannadasan, Acting Registrar, Mr. Lakus, Deputy Registrar, for their continuous support in all aspects. I would like to thank to Dr. Kannadasan, Principal, School of Pharmacy, for organizing the contemporary emerging trends topic in this FDP session. A special thanks to the organizing committee and technical support and promotion, Mr. Dev Singh and Mr. Arvind Verma. I would like to thanks to Mr. Gaurav Sharma, FDP Co-ordinator, for his efforts to make the event successful. Added to this, teaching and non-teaching staff for their unflinching support and coordinations. I would extend my heartiest thanks to all participants. With this warm words and a kind message, we move to the end of today's FDP webinar. Thank you.